Okay, several months ago, I was giving a lecture at an IB school, Resso IB in Helsinki, and some of the students asked me a lot of questions, and I didn't have time to go through all of them. One student asked me this question, which is that what is the most important equation in math? And now I'm trying to kind of get back to it and answer. Now, it's really, really difficult to answer this question because mathematics has so many different branches. The mathematics subject classification by American Mathematical Society has, I recently checked, something like 66 different active areas of mathematics, each of which is subdivided into, I don't know, 10 to 15 sub areas. So in some sense, there are probably like 1,000 different sub areas in mathematics. Each of them could be a topic for a PhD and in fact like a lifelong career. And everyone doing a career in mathematics probably has their own theorem which is most important. But I thought from the perspective of applications, because what does it mean to be important? Important that you can use it a lot. And of course, there are many theorems that are used in mathematics, and I would be happy to make many videos about that, and to tell you what's, in my opinion, the most important theorem in algebraic topology, or one of the most. Again, it's the same thing. Algebraic topology is subdivided into complex sub areas and so on. But I could spot some theorems that are mostly, very important there. But then if you go to logic, you have some other equations or theorems that are fundamental or central or are used a lot. And if we look at mathematics as a whole and we ask what is the theorem that is most, or the equation that is most used outside of mathematics, but also in mathematics, both, I think it would be the Central Limit Theorem. And let me explain first a little bit what it is and then why I think it's so important. In its simplest form, the Central Limit Theorem states that if you have random variables, so x1, x2, x3, etc., and you take their average, and so I'm using standard notation. So I define this x bar n to be the average of the first n of these variables. Like this. Let me just make this line look a little bit nicer. Then we know that this average is, for large n, its distribution is very close to normal distribution. So we can say that the limit of this as n approaches infinity is distributed as the normal distribution for some. I'm not going to go to the details in this presentation. There are many different versions of this theorem, but basically the point is that if we have random variables which are distributed in some way, it could be the distribution looks like this, but then you sum up them together and take and divide by their numbers, so like the average and average and average and average, it will approach the familiar Gaussian curve, which is difficult to draw. Something like this, okay? I mean, also, I'm sure somebody will dispute this and tell me that there are more important theorems in statistics, or more important theorems that have more applications. I don't know, maybe. So as I said, there are so many different theorems in mathematics and also in statistics. Like you have more fundamental theorem than this. Like for example, the simpler version of this, which is the law of large numbers. But anyway, so I think this is my bet on what is the most important theorem of all of mathematics if we consider in terms of applicability and in terms of usefulness. And the reason this is so useful is precisely because it does not depend on the shape of the original distribution. So it simplifies things. And so good mathematical theorems, they simplify complex things into simple things. Maybe a common misconception is that mathematics is actually very complicated. And yes, okay, mathematics is difficult, but the purpose of mathematics is to make complicated things simple. Like, whereas this distribution, which I drew first, is very complex, and maybe we don't even know its shape, and it might be completely beyond our methods or scientific, beyond our science to even find it. But if we know that we are summing up a lot of different instances of that same distribution, we know what we get. So in that sense, the analysis is tremendously simplified because we have an equation for this. We have tabulated all possible integrals of the, like, we know this upside down and backwards and forwards, and in every possible way. We're familiar with the Gaussian distribution, and because of this theorem, we understand why it, first of all, appears so often in nature. Not always. I mean, this is again one of the misconceptions of this theorem, is that Gaussian, like everything is Gaussian. It's not true. I mean, not everything is Gaussian, but when some variable is a average of many contributing factors, then it will usually be of this shape. So that's my take on that. Please comment below what you think and what is your opinion, or what is the most central or important equation or theorem in mathematics.